Cells in series. Physics for everyone welcomes you. Today's topic is cells in series. And next video we will learn about cells in parallel. In the next video we will learn about mixed combinations of cells. Cells in series. The main purpose of connecting cells in series is to get more voltages. Several cells can be connected to form a battery. First cell, second cell, third cell and fourth cell are connected one behind other. In a series connection, the negative terminal of one cell is connected to the positive terminal of the second cell. The negative terminal of the second cell is connected to the positive terminal of the third cell and so on. The free positive terminal of the first cell and the free negative terminal of the last cells are the terminals of the battery. Now here we have taken a 2-volt battery and another 4-volt battery connected one behind other in series connection. The current goes from negative to positive terminal. This is a conventional current. Next, we have taken a 1 coulomb of charge. When this charge goes from negative terminal to positive terminal of the 4-volt battery, it gains 4 joules of energy. We give a logical explanation. Now, the EMF of the second cell epsilon 2 equals 4 joule per coulomb equals 4 volt. Now, the 1 coulomb of charge goes from negative terminal of 2-volt battery to positive terminal of the 2-volt battery, thereby it gains 2 joules of energy. The EMF of the first cell epsilon 1 equals 2 joule per coulomb equals 2 volt. Now this is the equivalent single cell that effectively replaces 2 cells in series combination. Let us find this 1 coulomb of charge when it goes from the negative terminal to the positive terminal of the battery, it gains very well 6 joules of energy. Thereby the EMF of the cells in series effective combination ES equals 6 joules per coulomb. So the battery EMF is 6 volt. Good. ES equals epsilon 1 plus epsilon 2. The internal resistance equals R1 plus R2. Let us now consider the second cell is in the reverse connection. Good. Now the 1 coulomb of charge goes from positive terminal to negative terminal of 4-volt battery, thereby it lost 4 joules of energy. So the EMF epsilon 2 equals minus 4 joule per coulomb, and it goes from negative terminal to positive terminal of 2-volt battery, thereby it gains 2 joules of energy. So epsilon 1 equals 2 joules per coulomb. So totally the 1 coulomb of charge lost 2 joules of energy. Right? Here the loss means the direction. The direction means the current is reversed. So the battery is now reversed. Now the current goes from negative terminal to the positive terminal, that is from left to right. Thereby this 1 coulomb of charge gains 2 joules of energy. So epsilon S equals 2 joules per coulomb. So it is 2 volt. So epsilon S in the reverse connection is epsilon 1 minus epsilon 2. And of course, the internal resistance Rs is equal to R1 plus R2. You know very well the resistance does not depend upon the direction factor of current. So Rs in the first case as well as in the second case is the sum of the internal resistance of the individual resistance equals the effective internal resistance. Here first cell with EMF epsilon 1 and internal resistance R1, like that second cell, third cell, fourth cell and fifth cell are connected in the right order one after another in series connection. Now this combination connected to external resistance R in series, and thereby the current IS is formed. Suppose n cells each of EMF epsilon 1, epsilon 2, epsilon 3, epsilon 4 up to epsilon n, and internal resistance R1, R2, R3, R4 up to Rn respectively are connected in series in an external resistance R as shown in the figure. Epsilon s equals epsilon 1 plus epsilon 2 plus epsilon 3 up to it is epsilon n. So we can go with the summation. Epsilon s equals summation I1 to n epsilon I, whereas internal resistance, the effective internal resistance Rs equals R1 plus R2 up to Rn. So we go with Rs equals summation I equals 1 to n Ri. Now we have taken each cell with same EMF and same internal resistance for n identical cells in series. Es equals epsilon plus epsilon up to n epsilons. So Es epsilon s equals n time epsilon. So this is a very important equation. Let us rewrite here near the diagram. Epsilon s equals n times epsilon in series connection, and the internal resistance, the effective internal resistance of all the cells Rs equals R plus R plus R up to n times R. So we get Rs equals nR. Rs equals n times R. Now we have to go with current. Current is the total EMF by total internal resistance. We get n epsilon is the total EMF. The total resistance will be R plus nR, because the R external resistance and n time R the total internal resistance are in series connection. So the current Is equals n epsilon by R plus nR. These three equations are very simple to remember, and this will be used in solving the problem. So let us look at the Es equals n time epsilon, Rs is equal to n times R, Is is equal to n epsilon by R plus nR. Case A. If small r much less than capital R, if internal resistance is much less than external resistance, that is a fresh shell, then we have Is is equal to n epsilon divided by R, because here in the equation nR is very small, we have neglected it, and n epsilon by R, then we get a current n times I1. So Is when R is much less than R equals n times I1, where I1 is the current due to a single cell. Thus, if the internal resistance is negligible when compared to the external resistance, the current supplies by the battery is n times that of the current supplied by a single cell. So two things very important, I need to highlight it. One is when the internal resistance is very small compared to capital R, then the current is n times the current supplied by a single cell. Right? So the series connection is better when internal resistance is less, then we'll get more current. Case B. If small r is much more than capital R, internal resistance is much more than the external resistance, that is a used cell or a aged cell, Is equals n epsilon by nR. So here the external resistance capital R has been neglected. We get n epsilon by nR, which is approximately equal to current due to a single cell. Is when internal resistance is much greater than external resistance, then the current is current due to a single cell. Good. That is, current due to the whole battery is the same as that of current due to a single cell. Hence, there is no advantage in connecting several cells in series when the cells are used one or aged one. 2 points let us highlight. One, when internal resistance is much greater than external resistance, then current will be same as like single cell when more cells are connected in series. Good. Thus, series connection of cell is advantageous only when the effective internal resistance of the cell is negligibly small compared to the external resistance. The effective internal resistance of the cells is negligibly small compared to the external resistance. These are all the equations we have learned. Here we have n identical cell in series, but two cells, a group of cells has been connected in reverse order. It is shown in the red color. Good. Okay. If p cells in a group of n identical cells are connected with reverse polarity, then sigma s equals n minus 2p within bracket epsilon. S equals epsilon s equals n minus 2p times epsilon. Like that, Rs equals n times R. Right? Resistance does not depend upon the direction of current. So Rs, no change in Rs. So Rs equals n times R. Rs equals n times. Now let us go with the current. Is equals n minus 2p times epsilon. That is a total EMF by total resistance R plus NR. Thank you, children.